In today's lecture of mathematical modeling, I am going to teach you all the analysis of the prey-predator model. Okay, so let us start with it. So analysis of non-linear prey-predator model. If the value of all eigenvalues of J of A are strictly less than 1, then the system is stable, and if the magnitude of any one of the eigenvalue is greater than or equal to 1, then the system is unstable. Okay. So the fixed point of 1 is given by what? Lambda 1 is equal to 1 plus A lambda 1 minus B into lambda 1 lambda 2. Okay. Now lambda 2 is equal to what? 1 minus C lambda 2 plus D into lambda 1 lambda 2. Okay. By sorting this equation, what we get? 0, 0 and C upon D, A upon B has fixed point. Okay. Now let us see this. The Jacobian matrix is what? J is equal to what? Now let us see this equation. Okay, I have written this equation over here. Wait, let me show you all in the rough column. See, lambda 1 is equal to 1 plus A lambda 1 minus B into lambda 1 lambda 2. Differentiate this with respect to x. What you are going to get? Yeah, differentiate with respect to x. What I am going to get? 1 plus A, okay, minus by will remain, right? Now plug this value 1 plus A minus by over here. 1 plus A minus by. Okay. Now I have to differentiate this with respect to y and see what I am going to get. Okay. Now differentiate this equation with respect to y and see what you are going to get. So what I am going to get is nothing but this value will be 0. So I am going to get only minus bx, right? So minus bx. So write the value over there. So minus bx, this is how you all get. Okay, now this, take this lambda 2. Lambda 2, okay. In place of lambda 2, I have written y everywhere, okay. Now differentiate this with respect to x. What you all are going to get? Differentiate this with respect to x. I am going to get only dy, that too positive dy. Okay. Now plug this dy, the value of dy over here. Now differentiate that equation with respect to y and see what you all are going to get. Now differentiating with respect to y, let us see. I am going to get 1 minus c plus dx, okay. 1 minus c plus dx, plug the value over there. 1 minus c plus dx, okay. For the fixed point 0, 0, the Jacobian matrix is this. This is for the fixed point, okay. So I have taken this column to be 0 because if the value of x and y are 0, so for the fixed point 0 and 0, so x and y I have taken to be 0. So obviously this will be 0, 0. B value will be 0, x value will be 0, right? So 1 plus a will remain, 1 minus c will remain in this column, okay. And the eigenvalue are what? 1 plus a and 1 minus c will remain. Okay. So for the fixed point 0, 0 to be stable, modulus of 1 plus a is less than 1, or this 1 lies between minus 1 and 1. This 1 plus a lies between minus 1 and plus 1. So bring this, take this 1 the other side, so it will become minus 1 into minus 1, minus 2 less than a. So take this a, you will get what? Minus 1 less than a less than 1 minus 1. So you will get minus 2 less than a less than 0. Okay, this is how you all get this step. If we consider a greater than 0, then the point 0 comma 0 is unstable. Okay, then similarly for the fixed point, so similarly for the fixed point, C upon D and A upon B, J is equal to what? 1. This is 1 and 1, because so what you all have to do over here is, in this you all have to substitute minus b, what x I got, value of x is what? C upon D. Okay, minus b C upon D it will be. Okay, then dy, what is the value of y? D, then y, value of y is nothing but a upon b. Okay, and the eigenvalue are lambda is equal to plus or minus IAC. The magnitude of eigenvalue is greater than 1, hence the steady state is unstable. Okay, I hope you all can see this clearly. You all can take down the notes. So with this I am done with today's lecture, and thanks for watching. And one more thing, the previous lecture, this is a continuation of the previous lecture, that is the Jacobian matrix. Okay, you all have to first refer that. After that, this is the continuation of that. Okay, and thanks for watching.